entangled states lie at the core of different quantum technologies. For example, in optics, polarization entangled photons are readily generated using nonlinear crystals. In this video, we'll have a look on metasurfaces to create more intricate entangled states known as the quantum holograms. These quantum holograms have potential to enable high-dimensional encoding or to enhance communication capacity. The entanglement property of these holograms is also related to what we now know as the quantum eraser. First, when lasers shine on it, it can generate light field at a particular distance to form a hologram with HDVA lattice. Now the metasurface is used with a nonlinear crystal, the green box on the left. When one photon shining on the crystal is split into two, the polarizations are entangled with each other. The metasurface and analyzer further transform the silo arms polarization into two spaciable holograms psi L and psi R, which allow entangled with the left and the right hand circular polarization in the idler arm. For example, we design a metasurface to give two holograms of equal amplitude, but the phase difference will be decided according to steps of pi/2 for the different lattice in the hologram. Now suppose we have a vertical polarizer in the idler arm. The corresponding projection on the two photon states can be evaluated to be a simple sum of the two holograms. Is an interference destructive at the letter V because there is a pi phase difference between the two holograms in that region. Suppose we don't have any polarizer in the idler arm. In this case, we have to partial trace out the polarization degree of freedom of the idler arm. Then the evaluation gives us the summation of amplitude square of the two holograms. Interference gone.
In a real experiment, the signal photon will pass through the metasurface above me here and go to the single photon camera. Camera then count photon by photon and accumulate them to form hologram. On the idle path, the photon goes into the coupler here to the photon detector to make sure we are detecting both photons. We can then choose to insert a polarizer or not in this path to do the experiment. In fact, we have provided a visualization of the quantum eraser action. Here is a usual double-slit experiment interference. If we entangle another photon going to DL and DR detector and obtain rich slit information, the interference pattern disappears. If we insert 50-50 beam splitter before detection, the rich path information is erased and therefore interference pattern is restored. In our setup, the diffraction at the slits now become L and R hologram, while two detecting paths become two polarization channels in the idle arm. Then projecting to an intermediate polarization, such as a vertical one, we get back the superposition of two holograms, in the exactly same situation for the case of double slits. Such erasing action is visualized as a deletion of letter V. Here shows the different choice of eraser to delete the corresponding letters.